Hello, YouTube! Today we're going to be talking about mechanical energy. So we've already talked a bit about potential energy, we already talked a bit about kinetic energy. Now we're going to talk about why we care about those two things, which is that we can use the total of those two, mechanical energy, as a really helpful problem-solving tool for really quickly figuring out heights and velocities of objects that are going between two different places. So, end of the day, ideally you should be able to find mechanical energy and then use it to solve for information, especially if you're missing masses, which would make using forces a little more difficult. So, mechanical energy is in particular the sum of the potential and kinetic energy of two objects, of an object. And if there's only conservative forces, so like gravity or a spring, or well, those are the big two that we work with, or perpendicular forces that act on an object, your mechanical energy will be conserved. What that means is if you take the potential energy and the kinetic energy you had at the beginning, and as long as there's not something like a person or friction or a weird force that'll add or remove energy from the situation, so as long as none of that's there, your total of that potential and kinetic at the beginning and the end will stay the same. And what's useful about that is that when one type of energy reduces itself, which is a bit inaccurate, but when one of the types of energies gets smaller, the other one's going to have to get bigger because that energy has to go somewhere. But the total needed to stay the same, so it goes over into the other category. In particular, what graphs of this stuff will look like, if we've got a graph of potential energy as our sort of first line, if our potential energy looks like this in red, then our kinetic energy should look something like this in white. So this one is EK. And our mechanical energy should look something like this in gray, which is arguably the worst color for me to have picked there. That was somehow worse. We'll keep trying till we find one. Electric blue. Yeah, there we go. Our mechanical energy should just be a flat line throughout. When one decreases, the other one increases. When one increases, the other one decreases. And they go together. Now, this is only while conservative forces are acting on the object. If you get something with non-conservative forces like this, where like friction is slowing it down, then your mechanical energy will dip, and some combination of potential and kinetic energy will change to compensate for that. So you might get a continuation of your graph that looks something like this. Okay. The bullet points are on, we'll learn a lot more about the what a conservative force is. We will absolutely learn a lot more about conservative forces. That'll come in more when we're learning about work. Okay, so the equations from that. Mechanical energy is at the beginning is equal to mechanical energy at the end. That's all this first part is saying. Mechanical energy at the beginning, mechanical energy at the end. Great. Well, mechanical energy is potential plus kinetic. So if we take our potential and we add it to our kinetic, it'll equal our potential added to our kinetic. And so if we do that at both places, potential plus kinetic, I keep doing that backwards. Kinetic plus potential at the first location and the second location using the heights and velocities from those first and second locations, those will need to be equal to each other. And so basically what you're going to be doing for every problem this unit is running through a checklist, and this checklist will get progressively larger as we go throughout the unit. Is it moving? If it's moving, it'll have kinetic energy at this place. Is it off the ground? If it's off the ground or off of the point I specify to be 0, I being the person doing the problem, then it'll have potential energy at this point. That will need to be equal to the other types of energy at the other place. So at this second location or third location or fourth location, is it moving? Is it off the ground? And for every one of those things where the answer is yes, you have to include the energy equation of that type. In particular, if there's a third location, these things will all be equal to each other, which means that you could have 1/2 mv3 squared plus mgh3. And specifically because all of these things are the same as each other, you can pick and choose. You can choose to use 1 and 3. Or you can choose to use 2 and 3. Or you can choose to use 2 and 1. And those are all possible combinations. But you aren't stuck with just one equation or another. So just want to do a quick example problem with this and then call it. Pretty short one today. So let's do it. This one's short. Like this slideshow is short, but the stuff that you can do with this gets pretty extensive. So probably spend a day, spend 2 days, practice this stuff. And that's going to be a lot of it. So in particular, we've got a situation where we've got a pumpkin, and you're given the mass, but you don't need to be for reasons that we'll get into in a sec. Sorry. Great. So we've got this pumpkin. We know that at launch, the Vx is 10 meters per second. It's going at some angle we don't know and we're looking for, at some initial velocity at the first point we don't know, with some Vy at the first point we don't know, and it's going up to this place where at its maximum height it's gone 5 meters into the air. So if we think about this in terms of energy, we have a first location down at the bottom and a second location up at the top. Before I do that, I do need to use one little piece of kinematics that I want to be careful about. At the highest point, the velocity will be equal to the x velocity, because nothing's pushing this thing sideways. That'll be equal to the x velocity at the beginning, which we do already know is 10. So using our our energy equations, it's moving at the beginning. So I'm going to need 1/2 mv1 squared. But it's not off the ground. In fact, it's on the ground. So our height is going to be 0, and I can go ahead and not care about that potential term. At the end, it's moving, and it's off the ground. So there's going to be a potential energy term, and there's also going to be a kinetic energy term. But in particular, that kinetic energy is going to be the velocity from the velocity at the top, or Vx, which we know to be 10. For this one, we don't know what this velocity is. We know what one of the components is, but energy, and I should stress this about kinetic energy and probably should have earlier more, kinetic energy in particular is only going to use the actual speed of the object. Doesn't care which direction it's moving in. So you don't use just components, and you don't break energy up into components. You break it up into types, you don't break it up by direction. So as we're going here, if we want to find this angle, we know the x component, we don't know the actual diagonal, but that's what this is. So the only thing we're looking for here is this velocity. Well, we know the height, we know the velocity, so all we have to do is multiply each side by 2 and divide each side by m. 2, divide by m, divide by m. Now the mass over mass will drop from all of these, so we didn't actually need the mass, because when we get proportionately, basically being heavier means we started with more kinetic energy at the beginning, and also means that we'll need more kinetic energy to be going that speed at the end, and need more potential energy to be going at that height at the end. And so the two actually are happening in exact balance, and it winds up canceling. Almost done here. We've got v1 squared is equal to 2gh2 plus vx squared, square root. This might look a lot like one of the kinematics equations, and that's because you could solve the same problem with kinematics, but you'd be making some assumptions that might not always hold, so you want to really be careful on that one. So we've got that v1 is equal to the square root of 2 times 10 for g times our height, which was 5, plus our velocity of 10 squared, which will get us 100 plus 100, so 10 root 2 is our diagonal velocity at the beginning. And from there, because we know that this is 10 root 2, and we know that this is 10, you might already recognize the special right triangle, but we can take the inverse sine, we can take the inverse cosine, because it's adjacent, of 10 divided by our hypotenuse of 10 root 2. The inverse cosine gives us out 45 degrees, and that's our angle. You could have solved this one without using energy at all, but it's much quicker to use energy, so this is another tool that we can use for different situations. For some cases, like if something's sliding down a hill, you kind of have to use energy. You can't really conceptually use kinematics if the hill is, for example, looking like that. So, lots more to follow on these. The problems can get really intense and really difficult depending on what stuff you're combining with it. And, but for now, those are the basic ideas. Everything else is going to be using this and then putting it together with old stuff. Goodbye, YouTube.